And so yesterday we ended the session with the problem that barium is toxic, leaches out, so it will have impact either on the environment when you pour the water away, or it's actually really bad also for your process because your capacitor material is barium titanate. If you leave barium behind, you end up with a titanate, and of course it doesn't have the high dielectric constant of 5,000 or 200,000 for some of these compounds. So the key thing is then what we agreed upon yesterday, that we have to basically scavenge or steal the barium from the solution in some way. And let's hear a few solutions, what we came up with. And after we discuss them, we go into detail. And because we have here the theory spreadsheet, we can use actually the theory to calculate whether we have a chance to do it this way or not. Yeah? So you see how scientifically you can do this nowadays. You don't have just to guess anymore. But of course, yeah, the first thing is you have to propose solutions in a certain direction, and then you can go and check, and then you can also do experiments later on. So how do basically say scavenge barium ions from solution? So does anyone have an idea what we can do? Any suggestion?
If it is scavenge barium ions with the potential, we can attract them. Yeah, positive.
I mean basically apply electrodes into the system and then electrolyze the whole thing. The big problem that we have, we're working in water, and water typically you have oxygen or hydrogen coming out, or depending on the other ions are there, it's usually instead of oxygen, chlorine coming out. So the electrodes will not deliver barium metal. That won't work, unfortunately. And still then, we say, the barium would be lost for the process. You would then make titanate, and you can also start, okay, why don't you just make titanate process from the beginning? So, but yeah, good suggestion. So that was the first thing, so electrolysis of the system, yeah, but it's not being done, and it doesn't, if you look into detail, it doesn't make too much sense to go this route. Okay, other possibility. Very good. Put something else in the water reacts with barium. Okay. Add compound that reacts with barium. Okay. What do you know a little bit what type of reactions this could be, what you could do? No? Okay. So one thing is you can complex formation, yeah? And a complex, basically you have your ion and you put ligands around. Yeah, it's not, it's a different type of chemical bonding. It's called coordination bonding. But it's still a chemical bonding. Yeah. But we distinguish it for some other reasons. Okay. That will be one thing. The another thing is, of course, you can precipitate the whole material, yeah? Precipitation. And this would be insoluble compound, yeah? These would be the two main parts. And this insoluble compound can have two possibilities. It can basically just do the precipitation from solution, or it could also form as a subunit barrier layer on surface. Okay. So these are just two possibilities. There are others if we use different compounds. So, but this is now just staying with small molecules. Oh no, there's another one. Much more trivial. Yeah, so far we looked, this is a thermodynamic view. And of course, there must be something then kinetic. Yeah? Thermodynamic is basically tells you, you mix this reaction will happen, but it doesn't tell you how fast it will happen. So kinetically, you can also scavenge the barium ions. How can you do that kinetically? That's the first one we'll look into, because that's the easiest one. It's so trivial, you will scream when you hear it. Yeah, you filter it and pour away the barium ions, basically from the system. And kinetically is also, you do everything rapidly. So you do the dispersion rapidly, you don't get much barium out, and then you wash the system and get rid of the barium ions, and then process really fast after that, and then you don't have the problem with the barium ions. Yeah? That's actually a patent from industry, to just do everything fast and pour away some of the barium ions. Yeah? So wash and discard barium 2+ in a very short reaction time. Short. Okay. Of course, it means now you have to be rushing, and in a company that's never a good thing, because there are union contracts or other rules, and that means you prepare something, oh, lunchtime or holiday or whatever. So it's not the best way to process things, but it's a possibility if you want to get out of this problem. And so now you're back to these ones here. Let's say complex formation. I guess you've all have been doing laundry before. So you put a detergent in, and of course laundry suffers from calcium, magnesium ions. Yeah? Have you heard about that? The hardness of water. And if you have calcium, magnesium ions, first of all, some of the soaps get precipitated. Another thing happens with the soap, with the calcium, magnesium ions. They cross-link fibers in your fabric, and when you take it out, it's usually stiff. And so you want to get rid of much of the calcium and magnesium as possible, and you do the same thing as you can do here. You use compounds that form a complex, and there are some of them. One is called EDTA, and I'll write this now with another color on this side here. For complex formation would be EDTA, that is ethylene diamine tetraacetate. And this compound is, you can almost look at it like a spider, but it only has 6 legs, not 8. So it's actually more like an insect then. But it's a compound that has, okay, 6. I have only 5 fingers, I realized. It's a long time since I counted. So, and they have the ability to attack an ion and wrap completely around. Yeah? So basically, if one of these molecule sections, the acetate or the amine group, attaches to the barium ion, then the other one is so close by, it's also most likely going to snap in. And the other 4 are also close by, so they're going to snap in and bond. And this gives an extremely strong complex. It's so well masked, you barely can get it out anymore. Yeah? And this compound now contains a barium trapped inside, or the calcium, magnesium. You see, this very similar chemistry, same periodic part of the periodic table. And so it's not available as barium anymore. It's suddenly an anion because it's a barium 2+ versus tetraacetate, so 4- from here. And that makes it basically negatively charged compound. So if you look into the spreadsheet, the counter ion 2 plus is gone. And actually, if the material is still negative, you will have now, this is no longer counter ion because it's negative itself too. But this tells you something else. You introduce, of course, you always have electric neutrality. And this EDTA is typically a compound that is a sodium salt. So for each barium that you put in, you basically import 4 sodiums, or at least 2 sodiums. So you get some improvement in here, but it's not too dramatic. But we can see a little bit what it does. So there's a small processing window where you might be able to apply this. Yeah? So let's look at this. Typically, we have around 10 to minus 3 or 4 mole per liter of barium ions. Let's make 10 to minus 4. So 10 to minus 4 mole per liter of barium ions. And yes, so this would be without EDTA. And yeah, so we could still process this actually at this level. Let's see when it goes over. Let's take out, let's now go to 10 to minus 3. Yeah, now with 10 to minus 3, you are in the range. As I said, you have these 2 graphs here. This is the constant charge calculation. This is the constant potential integration. And you see overall that it's most likely not to be super stable, this whole system. So at 10 to minus 3 mole per liter of divalency, you basically don't have a system that is really good. And I'll show you this also, what it means in viscosity, because we haven't done the connection yet to viscosity. So what happens now if you put in the sodium instead of the barium at this level? Let's see whether this would work. So we say we put in sodium. So countervalent and valency is this. And sodium, we have at least double, if not 4 times. So let's just do double right now. And now look at the chart, what we have. So it's not much better yet. So this, at this level, it wouldn't do much. You see it's still attractive here, not really repulsive in the system here. Yeah? So let's see, how much would we have to add that we actually see some difference? So we would have to be also here probably an order of magnitude higher. Yeah, here now it's clear, so it would work well at this. If you maintain the barium ion concentration at 10 to minus 4 mole per liter, then this would work. And let's go back to whether it also works well for just barium. Yeah, it works actually for both well. So that actually tells you also something, that this approach that I said here, the complex formation, what do you think? Is this being applied? Is there a patent out on that? You see the calculation now. The calculation says there is not substantial difference. Yeah? So even though we can make a complex, it can really mask and steal the barium, we're not getting any substantial difference. Yeah? And that's why nobody does it. Yeah? So okay, so we attempted this. It's a clever idea to steal it and to scavenge it like this, but it does not give you really an advantage. So that's why now the only other 2 solutions here is basically precipitation and barrier layer. And I'm going to redraw the line. Let's see. Okay, you know, we're basically talking about these 2 parts now, barrier layer, precipitation. So I can wipe this out because I need the blackboard. And we need the spreadsheet also to put in the numbers. See. Okay, again we have here, actually I can go a little bit more to this side so I can leave it on the board, all the other discussions. So here's a log of barium ions concentration. And here we have pH scale. And at about 11.5 here, this is where vertical line goes up. And then at -4, so 10 to -4 mole per liter, this splits up a little bit like this. And then up here, here is barium titanate. Here is barium hydroxide, plus. And let me use another color now because we're going to a different compound. So basically this, of course, this line is connected with this other one. It goes like about this. And we come here to about pH, I have to go a little bit more over. pH 6 is here. And this is 0 here, yeah, at this level. Okay, so, and this region is barium carbonate. And barium carbonate, of course, depends on how much carbon dioxide is in the system, because carbon dioxide is in equilibrium with carbonic acid in water. And when you put in more carbon dioxide, depending on the vapor pressure of carbon dioxide, you can actually increase the stability region. Yeah? So this is at normal levels from the atmosphere, but if you increase it, then you can move it to this region here. Yeah. Yeah, so now you have a region where you can make it a barium carbonate layer into the system, and let's pick a point here. So we see now around pH or so, pH 8, we're in the range of 10 to -4. Yeah? So let's put this in. Yeah, let's go to this calculation here again. So we have 10 to -4, we have barium ions, and -25 millivolts is a typical number you can achieve on such surfaces. Yeah, so sometimes it's higher, -35, but barium titanate is really difficult to charge on the surface. And there's more details a little bit later why. So, but if you have this, then you see if you use carbon dioxide that you pump into the system and you work it around pH 7, 8, and so on, yeah, we basically can stabilize the system. And if you go even further over to pH 9 and so on, you're 10 to -5. So suddenly you can process the material. Yeah? If you add another 0 in here, yeah, now it's beautifully stable. Yeah? So, and up to pH 9, you're typically safe to work with. Carbon dioxide, it's not an issue to work with. Yeah? So that these are the parts that are really good. Let's also look now into processing from smaller particles. So far we had 500 nanometer particles, and of course nowadays the new processes require 50 nanometers or smaller. Yeah? So we need to add here a little bit in zeros, and let's see what we get now. You see there's still repulsion available, but it's not as large anymore as for the big particles. Yeah? So you see the smaller the particles are, the higher the potentials have to be then in order to do this, or less ions have to be available in order to make it nicely repulsive. Okay, so playing with carbon dioxide is one possibility. Why wouldn't you want to do this in reality when you do the process? Why is industry still not doing this process? What could be bad about carbon dioxide? And we're not talking about global warming here. It's too small of an amount. So I help you a little bit. So you have barium oxide plus carbon dioxide. It's in equilibrium with barium carbonate. And of course, this reaction can happen in both directions. And if you want to heat treat the material, what happens? You're moving into this direction. Yeah? So this typically, because you form a gas, is not really desirable because a gas causes bubbles. And in a solid material, bubbles means stress and finally breaking. If you do a rapid heating, you get so much carbon dioxide that you can put your system into little pieces. Yeah, so it breaks up. So you want to avoid a lot of the carbonate. Else you have to be really watching out how you heat. And if you heat a little too fast, you get too much carbon dioxide evolving, and then your part is lost. And in industry, of course, heating is not done in the lab where you have fine control and you can a little bit more. In industry, you have big burners, you check the temperature, and it can easily happen that the temperature overshoots a little bit at one point, and then you lose an entire batch of really expensive material. And once you actually made all these capacitors, you have, in some cases, even platinum, silver, barium titanate, and so on in there. And that's really expensive material, and to recycle it, to separate it and start from new again is very expensive. Yeah, so you don't want to mess up the process. Okay, so that's why barium carbonate is happening in the system, because there's carbon dioxide in the atmosphere when you work in water, but it's not intended, and typically they don't go the pure carbonate route. So what other things can we do? Barium carbonate is one possibility, but there are other salts that are really insoluble, and one of them is oxalic acid. Anybody heard about oxalic acid? Never? Who loves to eat spinach? Besides cartoon characters. You don't like it? Good. So why is spinach not liked? Does it have maybe something to do with this compound that I write on the blackboard? Yes, it does. When you eat spinach and a lot of other vegetables and plants out there, they contain oxalic acid. Spinach is rather rich for the things we eat. There are only a few ones that are richer. One is rhubarb. That's really acidic. That's why you put in tons of sugar to cover it up. And another one is super acidic and loaded with this oxalic acid is the cashew apple. Have you ever seen cashew apples? I mean, cashew nuts I've seen for sure, yeah. Do you know what cashew nuts are? Cashew nuts? These are, so maybe from spelling and pronunciation, cashew. These are nuts that are shaped something like this. And they should grow in Chile. At least they grow in Brazil. And that's a funny thing with this nut. And they're really common. Just go to the store. It's one of the common nuts that people eat. These nuts, they grow actually outside the fruit. That's also very special. So there's basically an apple growing on the tree, and at the bottom of the apple is the nut. Yeah? And so this cashew apple is also loaded with oxalic acid. And you eat it also as a dessert like rhubarb, tons of sugar in it, else you can't touch it. So, but what's the thing is, the oxalic acid, it grabs anything that is divalent, like calcium, and that's why when you eat the stuff, your teeth, you get your teeth coated with oxalic acid, because the calcium in your teeth is reacting with the oxalic acid in your spinach or on the other things. Yeah? And this is one of the reasons people don't like spinach. There are other reasons, but oxalic acid binds to your teeth, and you get some strange coating on there, which you can brush off then, of course. Okay, so oxalic acid binds well to calcium. Obviously, barium, similar group, also reacts really well with that and forms a very insoluble compound. Actually, it's so insoluble that the manufacturers for barium titanate work with oxalic acid. They have basically solutions of barium and precipitate them with oxalic acid and then react it with titanate. This is one of the routes to make barium titanate particles. And so we can use this here again. And let me do this here shortly. So oxalic acid is actually just a small compound like this. Yeah? It's a diacid, so 2 carbons, and acid-acid. Yeah? And with barium ions, you precipitate basically then barium oxalate. So it's barium 2 plus, and then CO, O. And this is, of course, 2, and here 2 minus total from everything. Yeah? Actually, this also, something like this. Let's sum it up. It's better to do it this. C2O4 2 minus. That's what it is. Yeah. And this is very insoluble. Much lower solubility than the carbonate. So what is the advantage here now? Because this also, when you heat it, it also decomposes into carbon dioxide ultimately. But why is there still an advantage to use this compound? Huh? No, it forms gas. But there's a decomposition reaction, so it has to interact with oxygen also. And that is a much broader temperature range. Yeah, so it's not as spontaneous and in a narrow temperature range. So you have an advantage that's a little broader. That's the main thing. So industry has an advantage. You have a little more leeway of things before things go really bad. Yeah. Okay, so this barium oxalate is very insoluble, so you suppress the barium ion concentration down to 10 to minus 6 mole per liter or so. And let's just put this in here now, 10 to minus 6 mole per liter. That means we have to add here another 0, or is maybe 2 more zeros. Let's see. 1, 2, 3, 4, 5, 6. Yeah, 6. And let's see. Yeah, see now, working with oxalic acid, you get a nice long repulsion no matter with which curve. So, okay, so with this, we can stabilize small particles. And of course, for large particles, this is for 50 nanometer particles, which you see is already much more challenging to get these potentials on than the large particles. Let's do this again now for the bigger particles. Let's make it 5 and 5. And you see extreme repulsion under these conditions. Yeah? So oxalic acid is a good compound to do that. And oxalic acid, because it precipitates this, it actually forms a barrier layer. Basically, barium leaches out, oxalic acid is present. You precipitate barium oxalate on the surface of your barium titanate particle, and you get a coating. The coating is dense enough that you hinder leaching of further barium. And if any further barium comes out, it will precipitate also. So it's actually a pretty good process to do that. That would be things. So we have now a chemical reaction where you can block that. So what other things do we need to discuss with this? One thing is we talked about these zeta potentials. And of course, there is a pH dependence of them. And there is also a relationship with how well these particles flow. And that's now something else we're going to discuss. We can get rid of this here. We don't need this anymore now. We can say, yes, it's fine. I need this and okay, and I need to turn off the LCD projector. Okay. So for processing of barium titanate, we saw we need a certain zeta potential. And a surface potential. Surface potential, zeta potential is used interchangeably in practice because surface potential is something theoretically accessible to calculate, but you cannot measure it. So the only thing you can really measure is a surface charge that is available under certain conditions, and that's what associated is with a surface potential, basically. Or zeta potential, sorry. So, and then we plot here what we can measure, the zeta potential. Zeta is a Greek letter, so zeta C would be the equivalent in English language. And so, of course, this is positive, negative. And this is measured in millivolts. It's a potential, really, then. Yeah. And we have a pH scale here. And as most compounds at a certain pH, they are neutral. And then in acid, they charge up. In base, they lose a charge and become negative. And for barium titanate, it's this way that you start out with a positive potential. And around pH 6 or so, you go negative, and then it becomes more negative. Yeah. So the positive range here is around plus 10 millivolts or so, plus 15 for barium titanate. It's usually not very high. And the negative part is around minus 25 to maybe minus 35 millivolts for barium titanate. It's never really high. And why is this the case? Let's say barium titanate. The reason is simply that barium titanate is not stable, as we've seen. So barium leaches out, and then barium reabsorbs from solution to the surface. Because barium is a so-called potential determining ion in the system, it means it's chemically interacting with the surface. It's really weird. On the one hand, barium titanate as a phase is not stable in water, and therefore you dissolve it. The barium comes out. On the other hand, it has enough affinity to the surface that it prefers to be on the surface compared to the solution. So you get barium ions reabsorbing to the surface, and that means when you keep barium titanate in water for some time, the whole curve looks like this. It's positive, and then a little bit more like this. And then you can have even this. Yeah? So barium titanate in water for 24 hours or so, yeah? 24-hour plus will give you such a curve here. And that also shows you this will be very difficult to process just with electric double layer stabilization, because the zeta potential is just 5 millivolts or 10 millivolts. And we didn't do this in the spreadsheet, but if you're below 20 millivolts, it's very difficult to disperse something. 10 millivolts is never enough. And especially barium titanate has a high Hamaker constant, so the van der Waals attraction is pretty strong. Yeah, so that's why barium titanate is a big challenge in the processing. So if we capture the barium and trap it on the surface without getting this additional charging effect, then we can process this. And oxalate was one possibility. So what else can we do now? Sorry. One more thing we need to talk about, and is the connection between zeta potential and viscosity, basically the flow behavior of the material. So what we have is always, let's just follow this up here. And we call it viscosity. So viscosity is the Greek letter eta, E, basically. Let's write it down, viscosity. And let's see. How do I plot this best? Yeah, let's just construct it for here. So let's do it like this. Baseline. Also pH scale down here, similar as up there. And we're going to focus on the black line here. So what happens if you're in this point here, when you use this spreadsheet for calculation, or just summing up what you have here, you have van der Waals attraction and no double layer repulsion. That means at this pH, directly down here, you will have the highest viscosity, means the highest resistance to flow, because particles stick together, and it can even be so high that it's a solid, so that you can't measure viscosity anymore, that it actually gives you solid state reaction, an elastic response instead of a viscosity. Yeah? So now, if we go to here, so 10 millivolt we said is not really dispersing, but it's a little bit better, so you expect that you get something like here. So this is one part of the viscosity curve. And now on this side, you see minus 25 or so millivolts, so about here is about the same as up here. So we need to draw it like this to here. And then from here, it goes down and levels out, of course. Yeah? So at this pH is no repulsion, therefore a sticking. Now you have some repulsion, here you have some repulsion. And the more repulsion there is, the lower the viscosity of the system. Yeah? And that's why for processing, if you can move it out to the higher potentials, then you get low viscosities. That's why we do this all the time. So, of course, there are now other chemicals out there that you can add. And we only focus so far on the electric double layer. What else can we add to the system is, of course, polymers. And let's shortly talk about what polymers can do. So let's wipe this out. Okay. So we can use polymers to stabilize slurries as well. And I told you already, for dispersion in organic liquids, polymers are actually used. We used fish oil the last time, basically, when we described this. And I told you we have basically a surface, and we anchor a molecule on there in some way. And there are now, of course, several ways of anchoring it and what the molecule does on the surface. Polymer is a large molecular weight. They're not always linear chains. They're sometimes also branched. They have a different number of shapes available nowadays. but most of the time you'd use the cheaper ones that are just linear or a little bit of branching. They're not necessarily always homopolymers. They're random copolymers, block copolymers, and so on. So right now, the first concept, we just look at the homopolymer and linear chain. And there are then basically possibilities how these things can adsorb on the surface. And the first thing would be just anchoring basically at the end here at one part of the chain and then having a coil. And that's actually pretty interesting because now you can calculate the size of such a chain just by statistics. There are several ways of doing that, and we come later on to this. So this system here where you have an anchoring at one point is called an chemisorbed or crafted polymer. Yeah? So crafted system. The crafting, of course, means if you do chemistry, you have to pay attention to the conditions. Chemistry, basically, if you work in water, certain chemicals don't react necessarily in this spot. So if you work in organics, again, then you can do that. There's another possibility, and that would be the physisorb, and that's the much easier one. And physisorb typically does this. So it has some chain ends that don't adsorb, something that adsorbs, some loops forming, something adsorbs, some loop, and another chain end. Yeah? So this will be physisorbed. And now there is, of course, the possibility when you have two surfaces approaching that you have different types of interactions. Let's do this when you have two surfaces. You can have then either a so-called, let's say here, physisorption and bridging phenomenon. Yeah, so it would be bridging. Or you could have, of course, if you have conditions where you have a lot of polymer present, so just physisorbed here. Yeah? So you have bridging, or the other thing would be stabilization. Okay, so the desire is now, of course, to maximize these possibilities of especially stabilization by maximizing the forces with the least amount of polymer. And what you do, you force systems typically into specific shapes. And you see the physisorb molecule here is a little bit more flat usually than the entire coil. So you can calculate it's really much flatter. The chemisorb is just also like a coil. So you're getting the advantage of the statistics of the coil, but you still can do something about it to force it. You basically want to put an entropic effect into the system to push it out and deform it. So what you like to do is then you form a surface where you chemicraft really strongly at a lot of dense anchor points, polymers, and that means you do this like this, and because the next one is crafted here, you see now the coils are deformed into long stretches. And this is an entropically unfavorable state because you have lack of freedom for these chains. And by doing so, you now get much stronger repulsion because these chains are entropically unfavorable state already, and if they interact with more entropically unfavorable states from the neighboring part, you get the maximum repulsion. So this is the approach that is decent for that. If you do work with physisorb, would be the same thing. You try to attach as many physisorb molecules as much as possible. The challenge is then to really get them to do this, that they also extend. And that is a challenge to do with physisorb. Typically, you can't do this. They typically do not extend much beyond what the physisorption does automatically. You don't have much control over this. So this chemicrafted is actually some possibility to give you the maximum repulsion. And yeah, so what are some of the polymers you can use? The typical ones that people play with is then, let's work this out. Is polyacrylic acid. And we have to say it's typically sodium salts that people use, yeah? So sodium salt. So the key groups in polyacrylic acid is basically you have a back chain like this, and then you have side chains with an acrylic, with an SOH acid function here. And here's, of course, an hydrogen attached and so on, yeah, and hydrogen, hydrogen. The same thing, yeah? And of course you have then a repeat unit here, like this. And this is a possibility for a good dispersion, and typically we said sodium salt, so this is actually gone. You have just CO minus, and then you have sodium plus here as a counter ion. Yeah? And this is used widely. And yeah, let's discuss what do you think for barium titanate. Would this be a good polymer to use? Would it work when you use such a polymer to adsorb on the surface? So it's a homopolymer. It would physisorb in some way like this on the surface. Let's say the one part is, I wiped out the chart. Barium titanate is typically quite negative over a range. So these are negative ions on the polyion system here. So that is not the best part. So, but it still will anchor on the surface. And as soon as you get barium ions leaching out, it will bind to the barium ion, which binds to the surface. So from that part, it will work. But there's another part coming for polyacrylic acid. And that is basically you have two chains here. And you have your carboxylic acid minus, and the same thing on this side here. CO, let's say the other way around. CO minus. Oh, sorry, this is a double. Then the other way around. CO, O minus. And of course, then here, if you have barium ion in between, you can complex those two. That's similar to the EDTA that I talked to you earlier about. Of course, you only have two groups now attaching to the barium ion, but this cross-links the polyacrylic acid chain, which means the polyacrylic acid acts like it's a higher molecular weight. And that causes the system to behave differently. Typically, you increase the viscosity, or you can even precipitate the polyacrylic acid if you have enough barium ions present. So polyacrylic acid works for dispersion, but it's not a really good dispersion because you have the chains that are supposed to stabilize here, can interact with barium, and you do not anything to hinder barium leaching out and so on. Yeah? So what else can we do then? We can move towards such a system, and that means we introduce chains that also can adsorb, and we use the repeat unit from here. So that would be a acrylic acid again, or methacrylic acid, depending on the synthesis of the material. So we have then a CO, O minus, and then here the backbone, and we have here CH2, and this here X times, and then we add another chain, and now it's an C2H2, yeah? And that is repeated here, Y times. So we form a block copolymer where you have a ethylene glycol. Oh, I need it here, another. An ethylene glycol here, and we have an acrylic acid here. And these two then form a compound that is basically, I turn this in red and the other one in blue. That is basically a short chain like this. And this part here is blue, a longer chain like this. Yeah? So this part here has still the features like this polymer, and it can anchor on the surface, a little closer to Chemi or Physisorb, basically, but Physisorb here is a pretty good description. And this section here typically doesn't anchor so well on the surface. It could also adsorb, but it's not so strongly interacting. And the nice thing is it's much more independent from barium ions. Barium ions don't bind or complex to the oxygens in this molecule. And now you have basically a chain that can extend, and you have a short chain that can adsorb, and you're coming to this so-called brush-like systems. Yeah? And with this, you can form really nice dispersions of this material, and you don't have to worry about the barium ion concentration. Yeah? So by moving away from electric double layer now to polymers, we have the ability to overcome the problems in water. So these are water-soluble, obviously, these compounds. You can overcome the problems that are associated with the dissolution of barium ions. Okay, so that was this part. And again, for these things, there are theories available. So you can do these things much more quantitative nowadays. So you don't have to just experiment with different molecular weights. You can actually calculate what size of molecules you will need to bond. There are theories out there. There are typically three theories that are used. It's the Monte Carlo simulations, basically. There's then the mean field theory, where you average everything. It's a thermodynamic approach. And then there's another thing is called scaling theories. And for these compounds, typically the scaling theories work best, since you're talking about small molecules. And with this, you can approach the calculations really the best way. Okay. Now again here, the potential or force, it doesn't matter. Let's plot the force right now. The force in between two surfaces and against distance between the particles. So we know generally we have, of course, this van der Waals attraction. Curve like this typically. And then we have, earlier we had electric double layer repulsion. And depending on the size of the electric double layer repulsion, it could be running like this, for example. Yeah? And then in the so-called DLVO theory that we had, we add these up, and then you get your joint curve. And that would be, for example, a curve that looks then like this, going up here. And then at some point, this is larger and dominates compared to this. So for DLVO, it always means there is a barrier formed. And then when you push it over the barrier, which if the barrier is too high, you can't push it over. But if the barrier is not so high, you can push it over. But let's say if you evaporate the solvent, or if you have water in the system and evaporate the water, of course, you're going to go over this barrier. Because first of all, when you evaporate the water, the ions that are present will concentrate, that will compress your double layer. So, and at some point, there's nothing there to repel anymore, so you stick. And so you can actually come to this primary minimum down here. And if you add water to the system again, it's stuck, because you have to get it out of this to back over there. And so you have to put in energy like grinding or milling. Yeah? So what is the big difference now if you use polymers? Polymers are very, very different in this behavior, because once you adsorb polymers, let's use black, they are stuck here on the surface, and they give you a maximum repulsive force, but it's there. And the force is especially present when you're directly on the surface. Then another thing happens. As you move out, it drops. Let me see that to make it correct. Sorry, I knew it's the wrong shape. Because it has to be forming an S, and that was not an S. So it drops. And then at some point, the polymer chain ends, and it basically drops off vertically. Yeah? So, and the interesting thing is now, when you add up these two curves, of course now this is a short polymer, you see it's not overcoming that. So if you add up these two, let's do this with, I don't have any other color, so I repeat blue again. Yeah? So of course, it would be then like this here. Now here this other force kicks in, and now we'll go up and up. And because this is here in close proximity, you will pretty much follow here. So there's maybe a shape like this or so. But the close proximity, the polymer dominates, and van der Waals forces can take over. So that means when you, should make it a little smoother, but when you measure these things, they really look rather bumpy. But that's okay, smooth stuff. So when you get in close proximity, this takes over. That means now if you evaporate your solvent, the polymer is still on the surface. If you add solvent again, it immediately repels everything, expands it. Yeah? And so if you work with these polymer chains, the beauty is now you can let the system dry, you add water, it's there again. You can basically play with this, and you don't have to worry. The electric double layer, once it's evaporated, you lose it basically. You have to start milling and everything again. So we have now several possibilities to disperse the system. And the next step after this would be to look into what impact does this have excuse me, on the final material. So the process after dispersion is, of course, casting. And so when we cast, we have to achieve a certain viscosity range, and you have to then dry the system, and then we have the printing and so on top. So the key thing is, of course, we want to achieve barium titanate, and we want to have the barium titanate really stoichiometric. Because barium titanate, when it comes into the final steps, where you now have the particles and they have to sinter together, that these particles have then to be of a certain size. And if you sinter particles and they are not stoichiometric, let's say you are barium deficient, 1 minus X, TiO3. So barium deficient, then you will be rich in titania. That means you are not in a solid state sintering process, you're in a liquid phase sintering process. We can't go there right now. All these things you need, it's a short time frame to look into the phase diagrams and so on. But you change the phase diagram basically here by moving to a titania-rich system. And this has a liquid phase forming at lower temperature. And therefore, when this material sinters, it is controlled by liquid phase sintering, which means you can get exaggerated grain growth under the conditions that you usually sinter, because you don't expect it to be barium deficient. The other thing, if you're exactly stoichiometric, basically here 1, and then 3, now you are in a solid state sintering range, and that means the gas phase transports, the diffusion control system is valid, and now you have exactly the grain growth that you want to achieve, so you get uniform grains. And yeah, if you have too much barium, you're still in the solid state process, but now you start to have doped systems, so you're not getting the system you'd like to have. So it's also not the best. So exact stoichiometry is really important. And this means it starts from the beginning when you weigh in your material, and through the entire process, whatever you do, you have to watch out that you don't lose the barium. And so this one process that we talked about earlier, where you just wash it and decant the barium ions, might be bad. You might lose too much barium. Of course, you can compensate by starting with something that is barium rich, and then 2% loss of barium ions wouldn't matter if you started 2% rich in barium ions. Yeah? So you can adjust for these things, but you have to watch out for a lot of little details. And yeah, with this now we are capable of making these capacitors. As I said, these things apply to any other aqueous processes where you put salts in. It doesn't have to be a salt. It could be tungsten carbide. It's also ceramic. And it will also interact. It will oxidize, actually, so it will give an oxide surface. If you put metals in like cobalt, iron, nickel, they also oxidize in water. You have then a ceramic surface. Similar principles are valid. You have, of course, also dissolution reactions, nickel ions or iron ions in the solution. And yeah, so it's valid over a whole range of materials that you can process in water, where you can block surfaces, you can add dispersants, or you can just mask the ions in the process. So the challenges nowadays, of course, we want to go to more energy stored in a capacitor, so you want to shrink it further, and what we talked about was particle systems. And with particle systems, you come down nowadays to around maybe micron size layers. So you use 50 nanometer particles, so you need to stack about 10 particles on top of each other to make a dense film without holes, because holes would allow for dielectric breakdown, and so you don't want to have holes available. So with 10 particles stacked on top of each other, 50 nanometers, so the lower limit for particle system is around 500 nanometers per layer. And that is not quite satisfactory, because you want to go thinner than 500 nanometers. So what other systems could you do then? Can you think of something to make it thinner? Of course, you have to go away from particles. So you have to go to vapors or to small objects you deposit, like sputtering. Yeah? So people go then to chemical vapor deposition, physical vapor deposition, sputtering techniques. And they really built already capacitors like this. They have in the order of like 100 nanometer, 200 nanometer layers of barium titanate or strontium titanate in there. But these are also now enormous challenges there, because now you're in a size range where these materials change their properties. First of all, barium titanate, if it's the grains that you have in there are smaller than 30 nanometers, are no longer in the tetragonal state. They're actually moving, they're changing phases over and become cubic. And in that cubic state, there is no high dielectric constant. Yeah? So that is a disadvantage. So suddenly your capacitor, even though you use the same material, drops dramatically in performance. Another problem is, we talked about stoichiometry. Of course, you don't have to go through a full sintering process with grain development in these methods, but you deposit your materials always in a certain oxygen environment. So it's a low partial pressure of everything, so you use a vacuum, of course. But the oxygen partial pressure defines how much is in this part in your equation. And of course, now your oxygen might not be stoichiometric all the time, so you achieve very different properties. And what people publish is actually then something on the order of maximum of 1,000 for the dielectric constant, but typically more on the order of 200 for the dielectric constant of barium or strontium titanates when you deposit them through these new methods. Yeah? So you see there's a lot of development still needed that you can make it to high dielectric constants. And the other problem, of course, is with all these things is they're very slow vacuum techniques. It's a layer-by-layer deposition. So if you want to make 500 layers, which is done in industry for the tape casting and stacking, you run really into the problem with the sputtering techniques. Yeah, basically one layer, that basically you have to put down a barium titanate layer, then a platinum layer as an electrode, barium titanate, and it's just, yeah, for a few items it takes forever already. So it's not feasible to make it on a large scale. And yeah, so typically the largest I found so far was in, when was it published? Yeah, it's about 6 years ago that was published. People had like 13 electrodes from platinum and 12 layers of the other thing deposited. So it's not a trivial. The other part is, of course, where do you get the sources from to evaporate barium? And you don't evaporate barium metal, you evaporate actually barium organometallic compound. So you have to synthesize these compounds first. It's also not trivial to make these, and yeah, it's getting more challenging to make these small objects. So that's why particle systems are still dominating in the mass market. Yeah? Okay, with this we're done for today, and yeah, thank you very much.